No worries. That was yesterday already. Yeah, welcome everyone to the second lecture. Yeah, I enjoyed it yesterday a lot. Yeah, you asked a lot of questions. I asked you to keep in this mode. Yeah, I mean, first part today will be a little technical. Bear with me. There's also exercises about that, so you can practice it a bit. And later on, I promise, I hope at least I can promise, we'll do some interesting physics, squeezing it out of that. So just as a reminder, yesterday we constructed, basically, we are already here. Yeah? We constructed out of the Lindblad equation this Keldysh functional integral. Now today we'll think about a specific limiting case of this Keldysh functional integral, improving over the limiting cases that we got to know yesterday. And in particular, we'll also give an answer to the a sharp answer to the question in which sense these systems we are thinking about in these Lindblad equations are really representing non-equilibrium stationary states, yeah? So in the stationary state. And then we want to once really go through this main goal that I advertised yesterday, namely connecting smoothly from a given microscopic physics to the macrophysics of a system, and we'll see under which circumstances really at large distances on the macroscopic scale, non-equilibrium effects can really start to dominate, even though on the microscopic level we just put a little bit of non-equilibrium perturbation into the system. Yeah? And for that we really need, for example, this theoretical development before. Yeah? So main task of today is to illustrate this transition here in a concrete and hopefully interesting example. So let me remind you a bit of what we did yesterday. So this summarizes this construction. We started from the Lindblad equation, which you can write out in this way here. We mapped it into a Keldysh functional integral, and the main takeaway that you should have here is that the structure of the Lindblad equation, this left and right action of operators, including the Hamiltonian and these Lindblad operators here, that's perfectly reflected in the structure of this Keldysh action that we got out. So if you take this home, it's already quite something. And here I've put you a few reminder definitions that you can follow through the lecture. So this is now relevant for this page. One thing that I also wanted to pick up, maybe that was not totally clear yesterday. I mean, I was maybe at times jumping a little bit between a continuum, a single degree of freedom, a lattice, and so on. So let me go through this here once again. So imagine we just have a single operator degree of freedom. Yeah? So a Hilbert space where I can walk by applying A and A dagger, just a single side. Then I'm a Hamiltonian, whatever it is, I can formulate it as a function of these two operators. Formally speaking, they span the algebra for this Hilbert space. And the Lindblad operators, same story. They can be arbitrary functions in principle of A and A dagger, right? So, and then we are here. Single operator, yeah, A. It translates into a field A of T, yeah? It can sit on either of these contours, yeah? So that's represented here. And it acquires a time dependence because we trotterize the entire evolution over the system. Single degree of freedom. Now, one step beyond, we go to a lattice system. Yeah? So there, we have an algebra of creation and annihilation operators on each side, which is labeled by I. And I noticed that at times I'm confusing a bit these notations. Yeah? Sometimes I label it phi, sometimes A. Sorry about that. It's a lot of slides. This translates clearly into fields now that carry this additional index I. And in the spatial continuum, very same story. Just think of this here as a continuous index, if you like. And here we have it on the operator side, and that translates into fields that live on time and space. Yeah? And one way of looking at that is that the notation you often see, this is a 0 plus 1 dimensional field theory, quantum field theory. This here, we are dealing with a D. Yeah? If space is D-dimensional, we are dealing with a D plus 1 dimensional quantum field theory. Yeah? But the essence of the construction, yeah? So this structure here, that this comes about, this is really encoded in a single degree of freedom, and adding the spatial indices is on that level just a matter of writing a little bit more. from the viewpoint of the physics that's going to happen, it's of course a totally different story. Yeah? So no one will doubt that 0 plus 1 dimension and d plus 1 dimension has extremely different physics. Okay, right, so far for that. And then the point I wanted to work for yesterday towards the end was to actually pinpoint to you specific structures of this Keldysh field theory, and the background of this is these considerations here. Yeah? It's about how do fluctuations surface in this formulation, and here the point of reference is this one. Classical field theories, as you know from mechanics, yeah? So Lagrangian mechanics, for example, is the physics of a single field configuration, namely the one that minimizes the classical action S. Yeah? And that is what we refer to as deterministic theories. Conversely, quantum and statistical field theories, they encode or they host a summation over all possible field configurations. Yeah? We're not ending with a single one that minimizes the action up there, but we really are imposed to sum over all possible configurations, and that's what's kind of illustrated here. Yeah? So there's this black one is minimizing the bare action or the classical action, this action here, in other words, and then there's more configurations around that that might also contribute. And that is what I would term, it's a quantum and statistical field theories, they are probabilistic in nature. Now, connecting this, if it wants to, Keldysh. Oh, Zoom is connecting again. Sorry, the Zoom has dropped out. It doesn't show here. It's here saying it's connecting to. So I. Cancel. Thank you. Okay. So we are dealing in general with quantum and statistical problems with probabilistic field theories. Yeah? So many configurations contribute. And yesterday we tried to look in the vicinity of this bare configuration, if you like. And to this end, actually a technical thing that we did, we went from this plus and minus basis, so these two Keldysh contours that we have, we moved via this unitary transformation here to a new basis, which bring out parts of this physics here, for example, the fundamental property of probability conservation more clearly as a property we could express as a property of the action that enters here in the exponent, expressed in the new basis. And then we also learned that this functional integral here, this Keldysh functional integral, has a deterministic limit, so a special limit in which really only a single field configuration would contribute, and that we got it by expanding this action formulated in classical and quantum fields here to first order. And that approximation was valid when, or a good approximation in the presence of a condensation phenomenon, and so a spontaneous symmetry breaking scenario where really the intuition is that there is then one very dominant field configuration, a winner takes it all, where all the particles are essentially gathering in a single bosonic mode, and that rationalizes why in this circumstance we get essentially a deterministic approximation to this entire Keldysh functional integral. And now in the first part of today, we would like to quantify the deviations. Now let's take this summation here seriously. How do we quantify that? Yes.
So I see the story very clearly now, but like just one question. So how do you identify like which field is classical and which one is quantum? Like, is it based, like sort of by definition that like you minimize the action for? So like, yeah, it's like I see those definitions, but I don't see like why do you call one classical and the other one quantum?
Very nice. We yesterday realized that there is a redundancy in this Keldysh formulation, which hosts this property. Yeah? And that tells us that this combination here, so assume now this mode here gets macroscopically occupied. Yeah? Then this sum over the two can also be macroscopically occupied. That's what we said. So this is the proxy for the, or this is how this formalism, yeah, we are developing the formalism, trying to interpret it. So this is how this formalism reflects a condensation phenomenon if this classical field here takes a finite expectation value. Conversely, we argued, well, if you look at the difference of these guys, and it doesn't mean that the field configuration phi plus, phi minus cannot be different, but their expectation values by this redundancy coincide. And therefore, this can never condense. So it's a kind of intrinsically only fluctuating variable. And that's what, so to say, gives rise to this terminology. Yeah? Okay.
So do you mean anything more than this, like when you denote it as classical versus quantum, like, or it's more like it's
terminology?
Okay,
There is actually in a limit of the Keldysh that we're going to discuss today. It's there's actually also a notion of field, just field and response field, yeah? And this is what I call quantum field. Is sometimes also called. I'm introducing standard terminology.
Okay, I see.
Okay.
Thanks.
Any more, guys? Okay. Right. So then how do we quantify deviations from the deterministic limit? Yeah, and there comes two important notions. Now this thing doesn't work. Correlation functions, again, a definition. Yeah? So they quantify, so there's two basic options, yeah, when we want to look at the expectation value of two fields. Yeah, it can be the classical expectation value and the quantum classical expectation value. Yeah? And what I want to argue now is that what we refer to, what we define as correlation functions, really quantifies precisely how strong are the fluctuations around the deterministic limit. While this other combination here, these are the so-called response functions, which describe the impact of an external perturbation on our system. So let's go through these things with these expectations here. Okay, and this part is a little technical. You exercise with it. Next comes more physics. Correlation functions, first thing. So origin of correlations are really twofold. Namely, they can come from quantum fluctuations, so non-commutativity of operators. Quantum mechanics is intrinsically probabilistic theory, and also in our Keldysh functional integral are, of course, encoded statistical fluctuations, yeah, which come from the fact, physically speaking, that many states, yeah, we don't discuss the physics of pure states, but actually a mixture of many states that gives rise to statistical fluctuations. Okay, now how do we quantify that? And to this end, we define a notion of a field fluctuation which measures really how far the configuration phi c is away from its expectation value. So, and remember, I mean, when we speak about expectation values of any polynomial here of fields, yeah, so then it's defined as an average with respect to this action here. Yeah, so this means, of course, immediately by definition, there's nothing deep, yeah, that the expectation value of this guy is 0, yeah, because if I take the expectation value of this, difference vanishes. However, if I look at the variance of this object here, yeah, so the correlation function, or the function, the average of the product of these functions, then this can take a non-zero value, and it will do so in the moment, yeah, so that in this configuration, phi here are deviations from the expectation value. Yeah? So precisely in the deterministic limit, this correlation function vanishes, and that really tells you that it quantifies the the amount of deviation from this deterministic path. So it quantifies the strength of fluctuations. And this is what is expressed in this, what is defined as now the Keldysh, so-called Keldysh correlation function or Keldysh-Green's function. So it's a function of two times and points in space, and it's defined like this, and you see that it quantifies, that it hosts in particular, it quantifies the strength of fluctuations. Okay, next thing, let's go to this other correlation or to this other object that so-called response functions, and that is the type of fluctuations that are coming in when the system is perturbed. So imagine we have an action here where there's a Hamiltonian part of it, can be this Lindblad action, and now I'm perturbing this Hamiltonian by putting on a little weak real-valued external field like this, which wiggles a little bit, which creates and deletes particles in the way that's prescribed here. Now, if we go through the steps and construct the Keldysh action for this problem, then you can see that this will lead to such a correction here in the Keldysh action. It's maybe a good way, a good point to repeat this. So here we have rho naught, and we have our two branches, and we have now a correction to the Hamiltonian that will sit here. So a delta H on this plus branch and a delta H that's sitting on the minus branch, and that will enter the Keldysh action via in the form of this Heisenberg commutator in precisely this way. And this is essentially what I've written down here. You see the difference of, for example, the dagger term here written out, and then the conjugate term is left implicit. The structure you should recognize here is that, interestingly, this external field that I'm applying in the Keldysh language exclusively couples to the quantum field. So you can see here exclusively the difference of these fields enters, and that's really due to this Heisenberg commutator structure. So the external field couples to this, what we just termed quantum field. Okay, and if we want to see how the system behaves when such a small field is switched on, we have to look at essentially the expectation value of, Fernando, can you maybe look this? Not really working here. Also it's fluctuating more than my Keldysh theory is. So it's a bit too much. Yeah. So so we can evaluate the expectation value of this field in the presence of the perturbation. So then we will have to evaluate the expectation value of the field within the perturbed action. And this we can rewrite it essentially as this expectation value here where fields occurs downstairs and upstairs. And if the perturbation is weak, so then we are entitled to expand this exponential. And to first order in the expansion here, we build up indeed this kind of strange correlator that I was talking about in the beginning, where there's one classical and one quantum field. Right, and just to go on here a bit, so this is the second piece that makes up, that quantifies, I mean, fluctuations in this system. This is this so-called retarded response function. So we have now, so that's the take-home message. We have two structures of quantifying fluctuations, and one is this Keldysh-Green's function, and the other one is the response function, which is essentially formulating linear response theory in this Keldysh framework. Now, let's try to get this more systematic and ask how can we calculate these different functions here. And to this end, we just formally introduce complex and contour-dependent fields. So instead of having here an external field H, which would not depend on, I'm really getting confused here. Yeah, please.
If you could go back 2 slides.
Yeah, please.
I'm sorry.
Sure. No, I'm there's many things flowing in here. I can only do one thing.
No, maybe like when you define and saying that the correlation functions have also source of classicality, like afterwards, after this slide. Yes, statistical fluctuations.
Yeah.
I was wondering about, first if you could elaborate, because it's not clear to me, many quantum states contribute due to coupling to the environment. It's not clear to me this connection between the two. The source of statistical fluctuations, this is the first question. And the second one is it possible to have a proxy of pure quantum effects, because it looks like correlation functions can have these spurious contributions. And so some sort of entanglement entropy analog or similar.
Yeah, so I think that to answer this comprehensively would take another lecture. I mean, one thing, I mean, a very plain thing, let me say, I mean, with respect to theories with statistical fluctuations, take an Ising model, write e to the minus beta h Ising, and then you see that, I mean, the partition function involves also summation of all possible configurations. And there's nothing quantum, there's no non-commuting operators, it's just up or down configurations of the Ising spin. Still, this is from a functional integral point of view, it's exactly the same thing as the quantum problem, because we have a summation that runs over many configurations. That is what I term statistical. Now, and in a quantum mechanical formulation, statistical means that we are dealing with an ensemble of states instead of just one single pure state. And then you can ask, so how is this expressed in the field theory, the purity of the state? It's actually a some sense subtle property, because the purity is measured by rho square or so. So it's beyond I mean, something that is linear in the dynamics, linear in the density matrix, as this formulation is here. But still, of course, there is some proxies in the field theory. For example, how states are occupied in the infrared in the long wavelength limit. And for example, for bosons, you can get a notion of classical versus quantum fluctuations, in the sense that in a pure state bosonic system, really only a single quantum state is occupied. There's no high infrared occupation of modes, while in the classical system there's a huge occupation of modes in the long wavelength or in the infrared limit.
Thank you.
Sure. Okay. Good. I mean, I can point you at some references for whether this is done. Okay. So we wanted to get a systematic grip on computing actually these correlators here. And so we introduced to this end this contour-dependent sources here, and then we can just as a formal observation, we can get all these correlation functions. We can get all these products of fields here under the expectation value by taking suitable derivatives and then setting at the end of the calculation the source equals to 0. So for example, the order parameter or the field expectation value, we get it by taking one derivative with respect to this J quantum here, and the single particle response function is just a second variation here with respect to quantum and classical field, which produces this combination of fields here. So this is the systematics, how to generate all possible, and including high order correlation functions. And then at one point in time, you have to sit down and make the connection to better interpret, or to further interpret them. You have to make the connection of these guys here to the operatorial formulation here. And if you like to go into the details here, I can recommend this review here. And these correlation functions, we generate them by taking twice a variation formally to this quantum source. And there's also then an expression of a relation to the operator formalism that you have to generate once and for all. And there's some extra information, namely in the limit of equal time and space. So this Keldysh correlation function, this gives you information on how the states at position x are occupied. That gives you just the expectation value of the local density. Okay, and in this way, you can assemble a total Green's function by going through all the second possible variations, and you build up this structure here. There is this Keldysh Green's function showing up in this entry, in the retarded and advanced. So when the star is conjugated here, built up here, the Hermitian conjugate to each other, Keldysh Green's function is anti-Hermitian. This entry here is 0 by probability conservation, again something that I cannot prove in this short amount of time. So here I go so that is what you should do in the exercises. You should compute correlation and response functions for a simple problem. So namely just a damped harmonic oscillator, quantum harmonic oscillator with here this oscillatory behavior and here a damping term. Your task will be to translate this into the Keldysh formalism and then compute the Green's function. And I think I leave it with this. This you can recommend to, or we do this on Thursday, then we read this in more detail and do these calculations here along the fly. Let me now get back to physics. That was pretty technical part. Please bear with me. So we want to now analyze really this big problem, where we have a spatial, d plus 1 dimensional driven open quantum field theory that, and I remind you, is defined here with this Lindblad operator, where the Hamiltonian here describes kinetic energy and two particle interactions. And the decay processes that we want to consider, or the open system processes, are a single particle pump, single particle loss, and these two particle losses here. We map this into a Keldysh functional integral, and then we get this beast out here. So this is also a very useful calculation that I advise to do. You start from this Lindblad action that I wrote down, and then you construct the Keldysh functional integral to begin with in this plus-minus basis. Then you perform the Keldysh rotation, and then you end up with this completely intransparent, I would agree, completely intransparent object here. Okay, so we try now to make sense of this and to approximate this a little further to really get access to what this physics, what this model here wants to tell us, or what this has to tell us. Okay, so let's go through all these terms. So here you can see the single particle sectors, and everything that is quadratic in the field here has here this inverse retarded and Keldysh Green's function showing up. And if you just do the manipulations I was describing, you find this expression here, where the interesting point is that this object here shows the distance from the phase transition. Remember, we had yesterday this picture that the qualitative physics of this Lindblad equation here was that when the pumping here starts to exceed the losses, so then the system starts to acquire a finite expectation value of the field. So in some sense, or in a very precise sense, this parameter gamma loss minus gamma pump, it measures the distance from the phase transition. Here is the phase transition for the onset of condensation. Here it's positive, and here this quantity is negative, this difference here. Okay, so and you see that in this sector here of the problem, the difference between, so this distance from the phase transition shows off. While in this Keldysh component here, that's also part of this quadratic action, the sum of these terms shows up. So in what the physical interpretation of this is that this here describes the level of noise in the problem, and so both loss and pumping contribute to the noise, so they should just sum up. And we want to go now through a simplification of this action. In particular, we will be able to drop a few of these terms here by taking a so-called semiclassical limit, which is a sharp argument, very close to the transition point where this is really going to zero, and provides a good physical intuition for such problems in a frequency regime where the frequencies are, where we look at low frequencies which are much smaller than this loss and pumping sum of them. And also in this framework, we're going to answer in which sense this qualifies as a non-equilibrium system. So that brings me to this part here. Yeah, so there's a question a priori that there is a phase transition. Right, so that is essentially this calculation that at least I described yesterday. Yeah, we looked at the expectation value of the field operator in our Lindblad phi-4 theory. We looked at its time evolution, and we found that it looks roughly like that, minus pump. Precisely this combination here showed up. Yeah, and then you can see, and then there was also some, yeah, so there's an I in front, but it cancels. And then there was some decay, kappa, two-body loss, kappa, this thing cubed, yeah, and we got here to a picture that we can write this as the derivative of a potential landscape, which looks like that, where this here, yeah, is a situation where gamma loss minus gamma pump was smaller than zero. Yeah? So therefore here the system settles down in one of these minima of the potential landscape. So here we clearly have a situation where the expectation value is non-zero. Yeah? So this happens whenever gamma loss minus gamma pump is smaller than zero, while in the other case, bigger than zero, the potential landscape in which this dynamics here takes place, should add an I here, looks like that. This is larger zero, and that means that the expectation value of phi equals zero. Yeah? So that was essentially the physics of this phase transition on a very simple mean field level. Yes?
I don't know if it's the correct moment to ask this question.
Let's see.
Just,
there is never.
So, this is kind of
always.
the mean field treatment of the
Yeah.
transition.
Mm-hmm.
So as you're breaking a continuous symmetry.
Mm-hmm.
You know, we are out of equilibrium, so I don't know, but okay, you still expect some Goldstone mode of some sort?
There is. You can literally see the Goldstone mode. Yeah? That's a very good question. I mean, I find it's one of the most important things is to always think in first place, yeah, in the phenomena that I'm looking at, is there anything specific to out of equilibrium or not? Yeah, and it's totally conceivable that there's a macroscopic occupation of a single mode. That's what happened, for example, in a laser. And indeed, yeah, so you can see here literally that it costs no action. Yeah? You just have to get away from the concept of energy. Yeah. But it still costs zero action, yeah, to walk around in this path here, while if you want to walk this way, yeah, it costs you action.
But then what about like Marmin Wagner?
Exactly this what we want to want to explore in the later part if we get to this point. Yeah. But no way. I mean, I encourage questions all the time. Yeah. So, but that's exactly the point. Yeah? So these phenomena, they are a little more subtle than this mean field, yeah? And you want to know what is the impact of non-equilibrium fluctuations. So exactly what we want to explore. Very good. Right, and this here is the platform where we can explore such physics. Yeah? So these are these exciton polariton systems. I just give you a briefly walk you through the physics of this system. So, and then we'll connect it to this Keldysh theory. Okay, so here in these exciton polaritons, we have what is called a quantum well. Yeah? So this is yellow thing here, where the main degrees of freedom that can be excited are particle-hole pairs, yeah, electron and hole pairs, which are called excitons. These guys, if you look what's their energy dispersion, how does E look as a function of momentum K, yeah, you find, oh, that's a totally flat function. Yeah? In other words, there is a huge mass, yeah, so they have a huge effective mass, a non-relativistic mass, which gives them totally flat energy dispersion. Now, then we put this quantum well between two very highly reflecting other pieces of semiconductor. And then the photons that are bouncing back, and we put photons in there that are bouncing back and forth, due to the confinement in this two-dimensional plane, they will not have a relativistic, so linear dispersion, but rather they also go quadratic, yeah, due to the confinement in one direction. Then people found ways to strongly make these light and matter degrees of freedom, so the excitons and the photons, interact with each other. And in this way, one finds the quantum mechanical phenomenon of hybridization. Yeah? So the effective energy dispersion of the strongly coupled light matter system is no longer these two dashed lines, but rather the effective energy dispersion are these two lines, the gray lines here. And then what people do, yeah, they shoot in with a big laser into the system, and they tune it to resonance, say, with this upper branch here. And these hybrid particles are referred to as polaritons. Yeah, so that's polaritons made of excitons, yeah, exciton polaritons. So people pump this upper branch here, and then this has some incomprehensible but effective loss processes where one occupies this lower polariton branch. So this gives you an incoherent feeding, yeah, feeding of this lower polariton density. And of course, this state of matter is not totally stable, but the polaritons, they will, due to the admixture of light, they will finally get lost out of this mirrors. But in this way, you can see there's really a kind of when you constantly pump the system, yeah, so that you can achieve, on average, yeah, so in a flux equilibrium state of these lower polaritons. So these are the relevant degrees of freedom in this problem. And how people describe that is not in terms of a Keldysh functional integral in first place, but rather they describe it in terms of this stochastic, what is known as stochastic driven dissipative Gross-Petaevsky equation. Complicated name. But here is what it means. One looks at the evolution of the amplitude of the lower polariton degrees of freedom. And if you look into this problem, yeah, you can see here, oh, that looks like a non-relativistic dispersion. So they just propagate here. They have a rotating frame, mu. And in particular, they have here this pumping rate is how strongly they are feeded from above. Yeah? The loss rate is how strongly they got lost out of the mirrors, if you like. They can elastically collide with each other. Yeah? So it's still quantum mechanical particles that can elastically collide. And then there's also, they get lost in pairs. Yeah? And there is this element of noise, which looks pretty innocent, but this is precisely the mechanism that drives you exploring a lot of configurations. Yeah? Remember, yesterday we looked at this mean field approximation, and all that was different in the mean field approximation to our Lindblad 5-4 theory was the missing of this noise. Otherwise, the structure was really precisely this equation. Yeah? So if you conceptualize this equation a little bit, yeah, you can see here that the time evolution of this polariton amplitude is driven by coherent processes, coherent dynamics. Yeah? So this is this propagation here. It has some dissipative irreversible dynamics, that's all the imaginary parts here, and is exposed to a random external force. Think of it like there is some random fluctuation, yeah, and that will always generate evolution or updates of this field phi, and kick it around. And this is precisely the effect, yeah, that describes how many configurations of this field configuration phi of T and X will be explored in the end. So that's one formulation how you can really get access to exploring configurations. So it should be somehow related to a quantum field theory. And now we'll see how precisely. How do we get the physics of such an equation here out of our Keldysh functional integral? Okay, but okay, before that, that's what we did essentially. Basically, so now comes what I discussed here again. So if we want to see how, indeed, in these experiments, people see a condensation phenomenon, here is again kind of what I said here now. Yeah? So if we simplify this problem down to the very simple most approximation, namely we drop the spatial dependence, we drop the noise just for really total simplicity, so then we see this at some point when the pumping exceeds the losses. the system starts to build up a condensation amplitude. Yeah? And the point here is, I mean, that goes exactly to your question. Yeah? So it really looks like a Bose condensation in equilibrium. Yeah? So at some point, we get a finite expectation value. It looks like a Bose condensation. So, but here we want to be a bit more accurate. Yeah? We want to first know technically how this model here relates to our Lindblad-Keldysh field theory, and also then, yeah, in which sense does this physics really deviate from an equilibrium problem? Yeah, so an equilibrium Bose condensation problem. Okay, and to this end, yeah, we first have to work a bit to simplify this action here, yeah, and so we have an ordering principle encoded here, which is available in the sense of a simple randomization group analysis. So who has heard about randomization group? So okay, very good. Yeah? So very nice. Yeah? So here comes now a very simple-minded randomization group argument that will enable us, yeah, to drop a few of these interaction terms. Yeah? And it looks like, okay, we are dropping 2 of them, but in fact it's a massive simplification. Yeah? But so let's see how it works. Yeah? So we're looking at these players here in the quadratic sector of the action, close to the critical point. Yeah, close to the point where the system starts actually to build up a condensation expectation value. We just said, yeah, so that this point is reached if the loss and the pumping become equal to each other. Yeah? So after this point, it starts to build up the condensation. So this means that this function here, yeah, it starts to show a scaling behavior exactly at the critical point where this constant terms here vanish. Yeah? Never mind about this. It's a rotating frame. You can forget about it. I should have put it to 0 to make it simpler. This function starts to scale with q square. Yeah? Conversely, this function here, this is a constant. There's nothing special. Yeah? If gamma loss equals gamma pump, that's just twice gamma loss. So there's nothing special about this function at the critical point. Yeah? And this leads then to a splitting of the so-called canonical field dimensions of the classical and the quantum field. Yeah? So they get different scaling dimensions. How you can see that? We work in the quadratic sector of the action, t and x, and we have this phi c star, which meets less than the complex conjugate of this, and then gamma loss gamma pump, or pk. That's how we can write it. Yeah. So this here is part of the total action. The total action, because it occurs here in the exponent of something, yeah, must scale like has scaling dimension 0. Yeah. So this is always, as one argues in randomization group, yeah, so a function here that's somewhere in the exponent cannot carry any dimension. Yeah. So it must scale like, for example, momentum dimension k to the 0. Yeah. And now we say this component here scales like, or q to the 0. This here at the critical point scales like q square, while this here, the Keldysh component here, scales like q to the 0 itself, yeah, because it just saturates to a number. Yeah? And therefore, the canonical dimensions, yeah, we now look for what's the power of this here. This will be d plus 2 halves, and this here will scale like d minus 2 halves, yeah, to make this whole action here dimensionless. Yeah, so even if you don't, follow, if you know RG, I think it will speak to you. If not, yeah, the upshot is that this structure, the splitting of the canonical scaling dimension of these two fields, implies that the nonlinear couplings of this theory here scale differently depending on how many powers of the quantum field are involved here. Yeah? And those are more important, yeah, that carry the least number of quantum fields because of the splitting of scaling dimensions. Yeah? And in particular, if you go through the calculation in detail, you see that, I mean, for example, this term here with 3 powers of the quantum field here, and this with 2, they are totally irrelevant in the sense of the randomization group, and they can be dropped from scratch. And this means, yeah, so that this really complicated action, it remains complicated but still simplifies a little bit. Namely, it only hosts terms, and that's now the structure we are aiming at, which is linear in the quantum field and quadratic. So that's all that remains. All these higher powers here by this RG argument, they are gone. And sorry, if this was not totally clear, if you don't know the RG, then, I mean, maybe we take this as a black box, yeah, so that, I mean, in the presence of near the critical point, we can drop a lot of terms. So that's the upshot of this slide here. Okay, now this is a calculation that you can certainly follow, even if you didn't, I mean, fully appreciate this argument, and that is that this simplified theory here becomes equivalent to this stochastic, to this Langevin equation we were just looking at. And now here comes how this works. We recall the structure of this action in the semiclassical limit, so where it's linear and quadratic in the field. And then we unintegrate this quadratic term here. Yeah? So let me show you what we are doing using this formula over there. So we go to this formula here, and we associate the sum over A as an integration over dt. So that's a continuum limit in time. So this is a general metric structure, but we can also think about, I mean, summations as integrations. Yeah? Then the translation is that this here is the variable psi of t that you find up there, and this thing here becomes phi quantum star of t. Yeah? So this A index is the t. This here becomes and this is here t prime, summation A and B over psi t prime, or psi t prime, plus this thing, where this correlator here, we take it as 2 over gamma delta t minus t prime. You see this formal analogy, yeah, so between the discrete version and the continuum version in time. And if you now just follow this formula, you will find that this here is realized dt t prime. And so this matrix here, A gets inverted. A delta function is like a unit matrix. It inverts again to a delta function. So here we have now phi q 2 gamma t prime, which is, of course, nothing like, we can drop this here. Yeah. And then you see, indeed, this is precisely this unintegrating, so integrating over the xi's here, produces precisely back this formula with this 2 gamma phi q star phi q. Yeah? So this is how we kind of unintegrate this quadratic term in the quantum fields. And then we do the same trick as yesterday, yeah, where we argued, this here, the integration over phi q, because we got rid of the phi q squared term, is now entirely linear in phi quantum, and we recognize this here, if you like, as a Fourier representation of a delta constraint. Yeah? So that was, again, I mean, the structure of this formula dp delta on x. So that's a Fourier representation of a delta constraint, this functional integration here over the linearly appearing quantum field. And that pins now the field configurations, as you can see, to obeying this equation of motion. And interestingly, there's only one difference to the linear theory, to the deterministic approximation we did yesterday, and that is this innocent appearance of the psi here. But this is precisely, as you can see very well in this formulation, here we are prescribed to sum over all the possible configurations of this noise that kicks around this field phi classical here and makes it explore all configurations. So then this is really equivalent, what we shown here, the equivalence of the semi-classical limit of this Keldysh field theory to the Langevin equations that I was presenting to you as a phenomenological model for these exciton-polariton systems. Okay, so a little bit of interpretation of this again. So we may look at this procedure as the semi-classical limit here now as a kind of weak occurrence of universality in the sense of loss of memory of details of the microscopic physics. So imagine here we started, or that's what we did. Essentially, we could start from this kind of theoretical Lindblad phi-4 theory, or we could start from some not totally well understood, but at some point quantum microscopic physics of exciton-polariton systems here. And we could coarse grain this to the very same description at mesoscopic scales. So at these intermediate scales, at the scales where we're describing these systems now, the system both of these exciton-polaritons and of this Lindblad phi-4 theory collapses on the same driven dissipative Gross-Pitaevsky equation. And the last step, or the next step that has to be, so you can see that many microscopic models really simplify and collapse onto the same physics at long wavelengths. So a phenomenon that you also know from equilibrium problems, it's known as universality. So such things here also happen in the in these out of equilibrium problems. And if one then wants to really extract quantitatively the physics at even macroscopic, at even larger distances, then one still has to do this final step, of course, graining this to the macroscopic scale, and that's what we're going to do now in a very concrete example. Okay, good. So here is a little bit an upshot and an overview of what we did so far. So that's maybe a point that seems important to me. So we started basically, so it's an overview of how different approaches relate to each other. We started from the Lindblad equation. We mapped this into an equivalent Lindblad-Keldysh functional integral. And then what we just did here, we mapped this Lindblad-Keldysh functional integral in a semi-classical limit, so close to a critical point, that's when this physics occurs, into this complicated Martin-Sigia-Rose functional integral object. For this object, we just showed that this can be related to Langevin equations in this way here. But it's really just parts of a bigger picture, if you like. Namely, you could, for example, also go, there is an alternative formulation, something that is equivalent or that is analogous to the Lindblad equation where we evolve the density matrix in a classical problem that would be evolving a probability distribution. This is known as Fokker-Planck equation. And there's also this thing here that we didn't discuss in much detail. There's a stochastic formulation for quantum evolution of operators, which is known as Heisenberg-Langevin equation. And the semi-classical limit of that, again, is Langevin equations. Now, let me point out the different structures that occur here. This here is a stochastic formulation of the physical problem, where there's an explicit noise entering the game. So this noise kicks around the field, and in this way makes the system explore many configurations. And that I would like to oppose to the deterministic evolution of probabilistic objects, which we encounter, for example, in the Lindblad equation. So there is no, in the Lindblad equation, we are really evolving deterministically. There is no fluctuating element in this evolution, but we are evolving a probabilistic object, namely the density matrix. If you diagonalize it, you get the probabilities for a certain state to be occupied. So there's always two kinds of formulation for a physical problem, with many configurations, deterministic evolution of probabilistic objects or direct stochastic evolution. And that's something, we'll encounter this tomorrow again in the measurement problem, so please keep this a little bit in mind. Yeah.
So just a question about like equivalences of taking different paths. Like say that you start from the Lindblad, then you do a truncated Wigner approximation. Do you get the same Fokker-Planck and then Langevin than doing the Keldysh path, let's say?
Right. So this is again, I mean, this is equivalent. What you know, this truncated Wigner is equivalent. I would really say to this here. To
but
this.
Like for generic problems, or you have to like look at specific like actions. And
I would say, I mean, well, as a specific in the sense that, I mean, I would dare trust it most for, I mean, bosonic theories, but otherwise you don't have to be very specific. So this truncated Wigner approximation is really precisely accounting for, I mean, it's really essentially the same thing as accounting for, I mean, in the Keldysh formula, it's exactly this truncating in the quantum field at second order. So that's really the mathematical statement.
I see.
And this in turn is equivalent to the Langevin.
No, because the truncated to me seems the truncated Wigner seems very obscure in the approximation.
It's precisely this truncation. So it would be pretty complicated now. But I think we can discuss this later. But that you can make this really sharp, so that precisely this quadratic term in the quantum field is precisely what is still taken into account in this Wigner approximation. But to explain this better, I think I should discuss this here in more detail. We can do it later on. Further questions, please. I mean, this is kind of an overview, so it's a good point to see. Okay. Yeah. Yeah, please.
Okay, so here we're going from Lindblad and formulating an action, an action that is straightly an open quantum system. So what would be the benefit of doing this versus formulating directly an action with a bath and then integrating out the bath of bosons or electrons?
That's, I mean, a very valid point. I mean, it's, you will find, I mean, I did this 1,000 times just to convince myself. It gives, of course, the same result. There are subtleties in how operator ordering and all of that. But I mean, in the moment you apply, I mean, this is a self-fulfilling prophecy if you don't do mistakes in your calculation. If you take the same assumptions, for example, this Markovian assumption, so this means that you make an expansion in derivatives of time, and on the action level, you get exactly the same action. What I would even advocate, in a sense, is that, I mean, if we start with the system bath setting, and then we can even go beyond the Markovian approximation. So then we end up in this, what is known as Feynman-Vernon path integral or so. So I would claim, or that's an obvious fact, so that this path integral approach is more flexible and can go beyond the Markovian approximation in pretty straightforward terms.
So would you mind elaborating a bit more again on this relation of like what we've developed here and like the Gross-Pitaevsky equation? I didn't quite get it.
Okay, so maybe then I go back to this slide here. So are we, this is okay, this step was okay. Then we had this undoing the integration. So I essentially, you can call this Hubbard-Statonovich decoupling. I just introduce another variable to unintegrate, to get rid of this quadratic term, because this quadratic term, this disturbs me when I want to do something like a delta representation of the delta function. But since we achieved that, so we have to live with the presence of this noise or this Gaussian fluctuations up there. But you see that this psi element makes it to the linear level in this phi quantum. And then we just do this argument. We use that this is a representation of a delta function, the phi q integration. And that is then sort of the constraint on the field configurations that we get from integrating out the phi quantum. And if you look at this thing, if you stare at it, well, this is just one realization. If you take psi fixed, it's just one realization of this driven dissipative Gross-Pitaevsky equation. And this thing here tells you, now take each of these configurations and sum over them weighted with this Gaussian weight. So this is really kind of it pops out, we didn't force it, it pops out and shows you the equivalence of this, and that's a conceptually important point, of this stochastic approach where we have an explicit noise, and this concept here, which came, if you think about it, really from this Lindblad equation, which is deterministic evolution of probabilistic objects. We took a semiclassical limit, and then we ended up here.
So, okay, so the relation is similar to like Langevin and, say, Fokker-Planck or something?
That's
like in a classical setting, say.
Yeah, let's see. That's precisely here. So the Fokker-Planck is indeed, I see this is the analog of the Lindblad equation. We are forward evolving a probability distribution. And you might see this Fokker-Planck essentially as a differential formulation of the problem, while this MSR functional integral is an integrated formulation. So you can think of this really as taking each step of the probability distribution, integrating this in a very similar way that we did it yesterday for quantum density matrix, and then we build up this MSR path integral as an equivalent integral formulation of the Fokker-Planck. So that's another interesting structure. So this here is a differential equation formulation. So that these here are differential formulations that look at how is the state updated in one time step. And these functional integrals here, you may look at them as integral formulations where we track the evolution over a whole time string.
Thanks.
Okay? Yeah, very nice. So because just remind me where I should go into more detail. Good. Okay, so what is actually non-equilibrium about these systems? And there is one thing that I should say very much in advance. So there's 1,000 notions of non-equilibrium. So it's a very broad thing. But I mean, there's two structures that you should, in your head, really not confuse. And that is, of course, one notion that was also Saro told yesterday: dynamics, time evolution of systems. So time translation invariance is explicitly broken. You want to track the process of, say, thermalization, or you have a driven system in the sense of, periodic variation of your Hamiltonian Floquet physics. This is not what we look at here. We look at a notion of non-equilibrium that is encoded in the stationary state. So what you should have in mind is a flux equilibrium state, and we'll quantify this more. And one thing I would like you to understand from scratch is that the decision on whether a system is in a stationary state, in or out of equilibrium, is not made by just staring at the density matrix. So because the density matrix, I can always write a Hermitian operator rho as the exponential of something. Something Hermitian, something other Hermitian. That's really any positive semi-definite Hermitian operator can be written like this. The decision of whether this is equilibrium or non-equilibrium is much more a question on dynamics, on what the generator of dynamics of this problem is. And you see that in the moment that you look at dynamical observables, not static observables, but dynamical observables. For example, a correlator like that, psi dagger of t compared to psi at t equals 0. So in this moment, when you look at two time points in time, you will see what actually generates the evolution of psi of t. And only if this generator is a Hamiltonian operator, will the system be in thermodynamic equilibrium? Anything else, like if you would imagine this is a Lindblad generator that acts on this psi, will automatically somehow push you out of equilibrium. The question is this significant physically at long wavelength or not? Yeah? But at a conceptual level, that's really it. Yeah? Thermal equilibrium is realized if the generator of dynamics coincides with this object that stands in the statistical weight. Yeah? And otherwise, we must expect non-equilibrium conditions, like in this Lindbladian. So a bit more hands-on. Yeah? This is a pretty abstract statement, but also general. Yeah? So I would like to understand that it's a simple point, yeah? But that non-equilibrium stationary state does not mean the system is just open. Yeah? So the question is, are we already in a non-equilibrium state if I couple the system to a bath? The answer is no. Yeah? So that is still compatible with the state of thermal equilibrium. The situation that really pushes you out of equilibrium is the one that we are realizing here in these driven open systems, when we couple one quantum system here to multiple baths, if you like. So all these so that's really the model that we looked at previously, so this workhorse model, where we have essentially very different dynamical resources, yeah, that different baths that we couple the systems to, and eventually the system really becomes confused and doesn't know which of these different baths it's actually supposed to thermalize to. Yeah? So by this is the incarnation of a driven open system. Yeah? We confuse a system of interest coupled to different baths, and the system just doesn't know to which one to equilibrate. Yeah? So there is certainly then some flux going through the system, yeah? But we want to quantify that. Yeah? And this is the next step. How can we really make this sharp? Yeah? How can I give you an action, and you tell me, is this an equilibrium problem or not? Now, how do we solve this? In field theory, we use symmetry. Yeah? So there is an interesting observation, yeah? So that, I mean, now take again, I remind you of this construction, yeah? Take the quantum master equation, so, and then we summarize this Hamiltonian part here. This is the action that we would have if there were only a Hamiltonian. Yeah? And then there's this dissipation going around, and that gives rise to this additional piece in the action. Yeah? So this is the Lindblad. Yeah? Okay, and let's now look at this artificial, or at this limit, yeah, where there's actually no coupling to a bath. Okay, so then, I mean, this dissipation part, the action coming from that is just zero, and we really describe an undriven Hamiltonian evolution, Heisenberg evolution in the path integral language. Now, here is an observation. This problem is invariant under this funky transformation of the field variables. Yeah? I have not a very deep interpretation of this, but it is an observation, yeah? So that this transformation here applied to the fields leaves the action invariant. Yeah? And if we have such a situation, yeah, if we have a certain symmetry in a field theory, or also in any physics problems, we have a certain symmetry, then we can look what's the consequences of this symmetry. Yeah? For example, translation symmetry, we know momentum is conserved. Yeah? Let's now, I just remind you what we are formulating in this field theory problem. Let me look at any observable, yeah, which I always can represent as a functional of the fields. Yeah, so then this is our huge Keldysh field here. I want to save a little time. Yeah, so this thing here, we can write it, I mean, that by definition, as a functional integral in our field theory language of this operator, functional on phi, is on phi. And I can do a transformation of variables, yeah, of the integration variable, as long as it's a unitary transformation t acting on phi. I can rewrite this as Yeah? So this is just a transformation of variables with a unitary transformation T. If we have a symmetry, this means that the action is unchanged. Yeah? So that's the essence of a symmetry. And if we are looking at a quantum field theory, we also want actually the functional integration measure to be invariant under this transformation itself. Yeah? Otherwise, we face what is known as anomaly, that the functional integral doesn't respect all the symmetries of the bare action. That's this one here. Okay, but then we can look at that, but then we just, okay, this is the original thing, this is the original thing. So what we get here is this structure. Yeah? So we get a relation between the correlation function symmetry transform must be the same as the original correlation function in the presence of a symmetry. Now, let me take this symmetry, yeah, which is just not translation invariance, but something else. Okay, it's reviving. So let's take this transformation and apply this logic down there. Yeah? And you find then that the word identities or the symmetry implications of this are precisely what is known as fluctuation dissipation relations of thermal equilibrium. Yeah? So it gives us, this is, I don't expect you to follow this in detail, but I give you this just as a statement that in thermal equilibrium, yeah, or that's how we define equilibrium, yeah, essentially as the presence of detail balance or on the level of correlation functions as a relation between the correlation functions that we discussed and these response functions, which universally for bosons goes via the Bose distribution in this way. The thermal equilibrium Bose distribution makes a sharp relation between the correlation and the response function as we discussed that previously. Okay? So that's the statement, yeah, so in one sentence, yeah, we can find in the case where the evolution generator is just a time-independent Hamiltonian, we can find a special symmetry of the Keldysh action, and this symmetry has as implication these fluctuation dissipation relations of thermodynamic equilibrium, and in this sense, really, we have found a symmetry behind the equilibrium state. Yeah? And again, the intuition for this is that if the symmetry is violated, yeah, if you now check for a Lindbladian, yeah, if you add something non-zero here that comes from a Lindbladian, you'll immediately say the symmetry is gone. Yeah, it's explicitly violated, and there is no such relation, and therefore there is no such thing as global detail balance or thermodynamic equilibrium conditions. And the intuition is then that indeed there is no global bath to thermalize to, induced by this Lindbladian. Was that a question? Yes.
So, like, if I'm given GK, GR, and GA, I can check whether.
Yeah.
But if I check at the single particle level, but can it be that I violate that in the multi-particle?
That's a very good question, but it's exactly the point. Yeah? So that is exactly the point that, in fact, you don't have to check each and every correlation function. You just have to check the symmetry, whether it's present on the action.
Okay.
Yeah? So it's much easier. Yeah? So I give you the microscopic input to your problem. You don't need to do any calculation. You just need to look at the microscopic input of your theory, and then you can test, you formulate it as an action, and then you test whether the symmetry is present.
But say that I measure something in the experiment, I measure some correlation function and stuff.
Yeah.
Then I, in principle, just by measuring single particle functions,
that you could also detect, I mean, deviation from equilibrium. So if you measure, say this correlation function and the response function, and you compare them, you look at the ratio, you will also see in this observable, yeah, whether these conditions are violated or not. Yeah?
I think there are cases where the single particle functions are okay, but
that's right. Yeah? So it's not. I mean, that's absolutely right. Yeah? So that, I mean, in principle, so there's maybe two ways. Yeah? So one way is more the theoretician's way. We look at the action test for the symmetry. Experimentalist's way, in principle, you're right. You have to build the whole hierarchy of correlation functions to test for the presence of equilibrium or non-equilibrium. Okay. The effect that you say is totally right. I have one piece of good news. In a good physics problem, it's never it's never necessary to go to the 50-point correlation function. The interesting physics is typically encoded in low-order correlation functions. And I mean, one intuition that you might have for that is that often there's some low density limit of excitations present, and you can compare this to, I mean, to people going on a ski piste. So the most probable event is single particle collisions. Someone hits a tree. The next probable is 2-particle collisions. 3-particle collisions is very improbable, and so we have it with correlation functions. The low-order correlation functions should host the important point. The higher order are less important, and that applies if we are not in a very dense situation of excitations. Of course, if you have skiers everywhere, it doesn't matter if it's 1 or 2 or 3 colliding.
Thanks.
Okay. 4 further questions. Okay, good. So we have now, and let me now bring this a bit more to life. So this complicated symmetry actually has a beautiful geometric interpretation. And that is what I want to discuss here. And this interpretation is strongest actually if indeed we commit here to the semi-classical limit of the problem, where we said, I mean, that's what we just derived. So the evolution here is generated by a reversible Hamiltonian. This is the kind of reversible processes, and these are or coherent, and these are the irreversible dissipative processes. And each of them can be packaged, as I told you in the beginning, in this kind of Landau-Ginzburg type functional. And now I'm just doing the following thing. Just follow what I want to do. I take all the couplings of this, say, reversible dynamics generator H, this Landau-Ginzburg thing, and I make a tick here on the real axis for the value of this coupling. Say this is the R, this tick here is the K, and this lambda is a real part of this here. And I do the same thing for the imaginary parts, so those that are coming with the dissipative terms. So this is a tick then for this K. This tick here was for the R, and this was for the imaginary part of the coupling. And the interesting point is now, when we look at the situation where the symmetry is present, then there is actually a constraint on where these couplings can be located. So in a driven open system with multiple bases, we have this situation. These couplings are spread anywhere in the complex plane of couplings. But in an equilibrium situation, the symmetry enforces all the couplings to be aligned. So that is another consequence of the presence of the symmetry, which is really very strong. So that, and I can give you an intuition for that. They are the reversible and the irreversible dynamics in an equilibrium problem is just not independent from each other. So imagine we start from a system that is microscopically totally reversible. So we just have a Hamiltonian to begin with, but an everyday experience is in our classical world around us, there's everywhere dissipation and decay, although the underlying physics is at some point, of course, Hamiltonian, purely reversible Hamiltonian dynamics. So let me illustrate this. We start on the microscopic level by a situation where all couplings are really aligned on the real axis because we only have Hamiltonian dynamics to begin with. But now we coarse grain to our more and more towards our macroscopic world, and what happens is that some dissipative processes will pop up. So we get here, we rotate a little bit out of this plane, and we get dissipative processes. And the point is that in an equilibrium situation, we preserve this microscopic alignment structure here, and this ray will just rotate out of the real axis, somewhere into the complex plane to describe dissipation. And that is really protected by this symmetry that we just identified, while in a driven open system, I hammer onto the density matrix of the system with very different external baths, and that causes these couplings here to bear no relation with respect to each other. So you can imagine each of these couplings here as being associated to a different physical bath, and that confuses the system, and that causes the spread in the complex plane of couplings. And
Sorry, so what do different colors represent here?
Right.
So those are like different baths, but like how do those baths differ?
No. Let's go back. It's very good that you're asking this. So we have here this alpha is the coherent or the dissipative part. Okay. And each of these parts has a kind of expansion in this Landau-Ginzburg. So another way of looking at that, so there's a relative I between those, and I'm now just plotting in this plane. Maybe I do it live to build it up, and I label this more accurately. So here I plot the real parts, so those that are really associated to this coherent part, and here the imaginary parts corresponding to the dissipative one. And now I look at the first one, R, C. So I put a tick here, and then for the RC, and I also put a tick here for the RD. So I get this. And now I go through this for all. The next is the K, the next is the lambda. So I get here so that's how I can do that. And the statement is, if we have the symmetry present, so if the system is microscopically, the dynamics is only generated by a time-independent Hamiltonian, then the symmetry, it's like another word identity. It forces everyone to be aligned on one line. So, and now we have actually really, and maybe I hope that I get through this. So now I would like to ask, so what is actually the consequence? So now we are kind of on a scale plot. So say here we are starting on the microscopic level, just to give you an orientation. We have now coarse grained, so this is length, increasing length. We coarse grain more and more. We have coarse grain to a mesoscopic level, where the semiclassical limit applies, and what we want to do, and here we have identified, okay, we see a crystal clear, mathematical difference at least, symmetry difference between an equilibrium and a non-equilibrium system. Now the question we want to answer, what's the consequence of that when we move to long wavelengths?
Sorry, just perhaps to clarify the previous point. So a naive question, but like, how does this connect to things like fluctuation dissipation theorem or something? So in equilibrium, that's what enforces that.
Perfect. This was just another, I didn't mention this name, or maybe I did, but this fluctuation dissipation theorem of thermal equilibrium is precisely, you can view it as a word identity of the symmetry.
Okay, I see, perfect. And then like non-equilibrium case, like there's no such case, and like you kind of, for each kind of like coupling, like you need to treat it independently, and like it will sort of like be,
there is, of course, there is some relation between the correlation and the responses. You can just look at the fraction, say, of this. But the point is, it will not be universally characterized by either the Bose or the Fermi distribution function. So it's just some weird non-equilibrium distribution function that sits between the correlation and the responses, and the universal special thing about equilibrium is that it's precisely Fermi, Dirac, or Bose, Einstein.
Okay, perfect, thanks.
More? Yes.
So this kind of, coarse graining procedure that leads to these complex couplings essentially is telling you that you have eventually like relaxation towards something, and it's connected to the fact that you have some flow from your long wavelength regimes. Am I right? This is how to interpret.
Right.
This,
so always, I mean, that's basically, I mean, also in a Lindblad equation, yeah, you can of course separate, I mean, reversible terms from the irreversible terms. So these are, when looking at the kind of really generator of coherent dynamics and its couplings, yeah, versus, I mean, the dissipative, versus the dissipative terms, yeah, so the rates in this problem. I mean, all I was saying that in the semiclassical limit, there's a very nice pictorial interpretation of the symmetry. Of course, the symmetry you can test it also in the fully quantum formulation of the problem.
But just to because there is this thing that is a little bit in contrast with what I knew, because here it looks to me that essentially as you are cross-graining, you have some processes that are taking you out from these cross-grain regimes, and this is why it's not purely coherent dynamics, but it's effectively dissipative.
Oh, and you mean that's what I told here?
Yeah, this imaginary part.
Very good. So
is it like this? Because
let me clarify this, because I mean here, what I was describing here is that a system can also act as its own bath. And so even, I mean, you know this phenomenon because it's a world around us. Yeah? So there is some underlying quantum Hamiltonian. Still, everything here is dissipative. And this means, so that the system, even if you don't have explicit baths coupled to the system, it can act as its own bath. The picture is actually high momentum modes. They act as a bath for the long wavelength modes.
Because this, I mean, generally, like if you have a purely coherent dynamics, expect locally to equilibrate. And so this long wavelength limit looks to me that is instead globally is telling you that is equilibrating.
Locally, it fits to my picture if we specify locality in momentum space. So, I mean, my picture is... I mean, when you say locally, let me formulate this slightly more generally, looking at subsystems. So if you look at, I mean, the wave function of the universe is always in a pure state, trivial. But if you look at any subsystem, you will see things. So you will see, for example, effective thermalization and so on. And so the subsystems that are often chosen are in real space, but I may also choose subsystems in momentum space. And the picture with these long wavelengths is to me mainly this. I have shells in momentum space. I like this RG arguments. So here you have a shell in momentum space. You integrate this out. This is one of your subsystems. I divide my system into subsystems in momentum space, and I compute the effective action, so which is in the subsystem here. And when you do this more and more, you arrive really at this coarse-grained theory. And this coarse-grained theory will show you dissipative behavior. Because we're decimating subsystems by integrating out momentum shells. I mean, mixed states is physics of subsystems.
No, absolutely. It's simply that it looks like this coarse-graining is the subsystem is larger and larger in real space. And so it's kind of, I mean,
yeah, but we are discarding at long wavelengths. We are discarding physics at short distances. So in that sense, it's also a subsystem. So I think that's the resolution of this.
Okay, thank you. No, now it's more clear. Thank you.
Okay. Right. So.
Maybe we can stay a few more minutes.
Okay. So I think I would like to, to show you at least. How this goes. There's a fulfilling finally the promise that I didn't bore you here with complicated formulas and then not coming to the point. So, okay, so let's look specifically at phase transitions in 2 dimensions. That's what I want to focus now to illustrate this last step of the transition from micro to macrophysics. Okay. And so, and let's look at systems phase transitions in 2 dimensions. Systems with a phase rotation symmetry U1. So that's what we had in our microscopic workhorse model for sure. And I give you here just the facts. If you look at, there is in the low temperature regime of these U1 symmetric systems, so there is no spontaneous symmetry breaking, but a phase transition. And this phase transition is between a low temperature regime with algebraic correlations and a high temperature regime with a more generic exponential correlations between systems. Yeah. Who is aware of this actually? Who has heard about this? So this is, okay, good, yeah, so that I know. So this, and in between this low and high temperature phase, yeah, there is what is known as a Berezinski-Kosterlitz-Thouless transition, which can be understood. We won't make it to this point, although it's interesting, to unbinding of vortex anti-vortex pairs. Yeah? But no matter. Yeah? So the interesting feature for this first part here, or what I still would like to discuss, is the presence of correlations here, which are algebraic. Yeah? So, and we want to know what is the fate, essentially, of this transition scenario of this physics here in an out-of-equilibrium system. And now, I want to give you a little background. Where does this algebraic decay come from? Yeah? Usually, you would say, I mean, if you look at an ordinary system, high temperature, you just have short-range exponential correlations. Here, I'm claiming there's at low temperatures, there's an algebraic decay of this correlation function. And here is the reason for that. The reason is that in the low temperature regime of these problems, we have gapless excitations. Gapless excitations are spin waves, yeah, on this, or Goldstone, almost Goldstone modes, yeah, that are sitting around, yeah, and that are described by an action that looks like that, gapless. Yeah, so there is no constant term. The first term in the exponent of this action comes with a gradient. Yeah? And I can write this as a q square when I go to momentum space. Now, what does this gapless nature of excitations mean? I can, again, it's a disaster. Yeah, so I can compute this or estimate this correlator by going to a phase amplitude decomposition. So I decompose it into density fluctuations and phase fluctuations. Yeah? With the idea, yeah, so that the phase fluctuations, they are gapless, and they should be active still at the large distances of this problem. Yeah? And that is what we can verify in this calculation here. We approximate this correlation function here essentially only by the phase fluctuations, yeah, while these density amplitude fluctuations, we approximate them as we neglect the fluctuations of this degree of freedom. Okay, and if you use magic Gaussian identity, you can derive it from over there if you like. You find that this correlator here boils down to evaluating the two-point correlator of these phase fluctuations. Yeah? So this object here, and this object turns out to have a logarithmic divergence, yeah, which comes from the long wavelengths, from the low momentum modes. And if I insert the logarithm here in the exponent, yeah, you see, oh, this gives me precisely an algebraic decay. So summary, the spin wave excitations, the gapless fluctuations in this problem, give rise to an algebraic decay of correlation functions, and that's a super universal effect of two-dimensional systems with a continuous phase rotation symmetry. And this is what we want to now challenge. Yeah? How is this behaving out of equilibrium? So we want to know the fate of this, what is known as algebraic quasi-long-range order. And to this end, yeah, we are now very flexible with formulations. Yeah? So one nice formulation is this driven dissipative Gross-Pitaevsky equation, and we do something pretty simple. Yeah? We do just this phase amplitude decomposition here. And then we integrate out the density fluctuation. So if you like, we go from this stochastic GPE equation, Gross-Pitaevsky, down to something a little bit more coarse-grained, which has integrated out the short distance fluctuations of density. They are only active at short distances, so we can just integrate them out, adiabatically eliminate as you like in language, and then something interesting happens. Yeah? This equation pops up here, and this is a very famous equation, yeah? So-called Cardar-Paris-Zizang equation. Yeah? I will tell you something about that. And this describes the linear term here, describes the diffusion of this phase, and then there is this phase nonlinearity here. And there's also some noise in this problem. And the meaning of this is, yeah, so that this linear spin wave, so that is what we had at equilibrium, so that is essentially the equilibrium theory I was presenting previously. This is now equipped with a nonlinear term, yeah? And the fun point is this nonlinear term is exactly forbidden by symmetry if we are at equilibrium. Yeah? So if we are in this situation, there is a symmetry that, that forces all these couplings to be on one ray, you can convince yourself that this lambda nonlinearity has to be exactly 0. Yeah? While in an out of equilibrium situation, there is a spread in the complex plane, and that allows for non-linear, for non-vanishing lambda. So we have a single parameter measure for the presence of non-equilibrium conditions. And let me just, the last thing, I skipped that, relation to this original problem. Here is what we then conclude from that. Yeah? We start from this coarse-grained KPZ description, and then we can run down the RG flow, studying how important is this lambda parameter when we coarse-grain to the macroscopic scale. And that is summarized in this plot here. You can do this in different spatial dimensions. Yeah? And the trend is, yeah, in high spatial dimensions, this coupling lambda here, this non-equilibrium measure, shrinks to 0. So that means in high dimensions, we are approaching lambda equals 0. We are approaching an equilibrium situation. So in some sense, in high dimensional systems, equilibrium conditions recover when you go to long wavelength. But in low dimensions, it's exactly the opposite phenomenon. Yeah? Even if we go with a very small coupling out of equilibrium, we break equilibrium conditions a little bit, and then we coarse grain towards the macroscopic scale, you can see that this coupling becomes more and more large, and in this way the system will behave more and more strongly out of equilibrium. And if you look at the consequences for this correlation function here, you can see the following thing. At intermediate and short and intermediate distances, the physics will still be governed by this algebraic decay that we know from equilibrium. But at some point, the system, at some large distance, the system notices it's actually out of equilibrium, and then this paradigmatic behavior from equilibrium systems of quasi-long-range order in 2 dimensions, low temperature, is really cut off, and non-equilibrium systems do not, so to say, fall into this very same universal behavior as equilibrium systems. So that's illustrating the point. I'm sorry that I really took a bit more time. And tomorrow we go into more quantum applications of this Keldysh path integral in the frame of measurement theory. Thank you for your attention, and thanks a lot for asking so many questions again. Yeah?
Okay, thank you, Sebastian. So I think that we can still go for 1 or 2 questions if there is some. Yeah. There is one in the chat.
Not sure I can find the. Right, yeah. So I mean, so we up there on the board stands this correlator. And as I said, we can approximate this here by its phase fluctuations. Yeah? So it's something n0 e to the minus 1/2 theta phase variable at position r minus theta position 0, this thing squared, and then the expectation value of this. Yeah? And we have to evaluate this correlator here at equilibrium. It scales like a log of r, yeah? Giving then rise, as I was arguing in the beginning, yeah, to, I mean, e to the log is a power of r, yeah? This power of r here, while, so this is the equilibrium limit, yeah, or the equilibrium. So the logic is this. Somehow here we are evaluate at short enough distances, yeah, below this scale here. We are approximating this. We are pretending the system is very well approximated by equilibrium physics, and so on these distances we get a log behavior of this phase correlator. Now, at distances way above this length scale here, we pretend we are very close to this new strong coupling non-equilibrium KPZ fixed point, as it's called. And then we have to re-evaluate this correlation function. What are the field dimensions of these operators here? Yeah, and you find then that those behave like r to the 2 chi, and that is what is known as chi is the scaling dimension of this field variable here. So you can see a very different qualitative behavior. At equilibrium, there's a log growth of this correlator. At non-equilibrium, so close to this new KPZ fixed point, there's an algebraic law, but this algebraic law occurs now in the exponent of the correlation function here. And you see this behavior, so that's here e to the r 2 chi. That's really evaluating, in one sentence, evaluating the phase correlator at these strong coupling fixed point, this so-called KPZ fixed point. So that gives you the scaling, and it is sub-algebraic. It's a stretched exponential decay.
Okay, so we are a bit out of time, I would say.
I cannot see the pointer, but I think I am. Okay. If not yet, you can just ask again. Yeah.
Okay, thank you. So we can go for the coffee break, and I would say that we can come back at 11:40 with 10 minutes of delay. It's okay.